Hi, in this video I will now demonstrate how to run a regression in Stata. You all know how to do this from before, but the purpose is not just to show you how to run this regression, but it's just to talk about what omitted variable bias could cause, and what we should do when we suspect that our regression coefficient estimators are suffering from omitted variable bias. So and then we did in the class, in the last class, I think we did an example, and then there were a number of you who told me to record the video on this again. I think it's because of maybe we had to go over it very quickly, and then there were a number of you asking questions. So I hope this video then answers your questions. So I'm going to go to get the fetch the file from my drive. This is the college distance file, and when you import it, it's an Excel file, so you have to import it into Stata. You cannot just open it because Stata opens only Stata data file. So this is an Excel non-standard file for it. So you go File, Import, Browse, and then you have the data here, preview of the data. You will see that the data has each of the column is basically a variable, and the rows are observations, or in this case there are how many students, I can't remember. There are more than 500 students here, and these are basically interviewed students. The person is where the person is male or female, so their gender. If a person is female, then they will take this variable takes 1, otherwise 0. So this is a binary variable. The same here, a person is black or white or any other race, and if this person is black, it will take a 1. So observation will take 1, otherwise. And then the same here, Hispanic. And I think these are test scores which I didn't study, didn't bother to look at, but I hope you will be looking at it and studying it before you go on to interpret your results. Let's say for this one is also a binary variable. That college, if a student's dad or father had a college degree in the family, then this variable would indicate that this person's dad had a college degree, so that's 1. And then there are a number of students here whose dad didn't have a college degree, and so it says mom college here, so it's if where the person's student's mom had a college degree or not. So read this. There's a description of these files which I should have read, but I didn't. But I hope you will read them. And this one here, own home, is where the person's family owns a home or they're renting it, so sort of thing, right? Okay, let's tick this box here to make sure that the names of the variables do not appear as observations. So now you see the names, names are there at the top here in the variable name box here. So let's click OK. Right, so it's now all here, official. Now I need to just type in the regression equation, how I want to run it basically. Now let me give you a quick introduction as well, again, what we're doing here. So I'm reading it from your question number 4. This is question number 4, class number 2. So on QM Plus, you'll find a data file, college distant Excel, that contains data from a random sample of high school seniors interviewed in 1980. So there's first interview, and then they were re-interviewed in 1986. So in this exercise, you will use these data to investigate the relationship between the number of completed years of education for young adults and the distance from each student's high school to the nearest 4-year college. Now, proximity to college lowers the cost of education, so that the students who live close to 4-year college should, on average, complete more years of higher education. So distance matters, in other words. And the detailed description is given in the QM Plus file, college distance description PDF. Now A, run a regression of years of completed education, ED, on distance to the nearest college, dist. So there are two variables, ED and dist. And dist is measured in tens of miles. Education is the number of years of education completed. So a number of students asked what the measure of scale was in here. It is tenth of miles. So and then we'll have to report the estimated regression with the standard errors R squared and SER. Okay, now reporting is basically taking a note of what you have just found. I don't think I'm going to report it. I'll just highlight what you found. I don't have the pen tablet with me now. So let's start and see how it looks when you run the regression. So the command for running regression in Stata is rec and followed by dependent variables, so ed, and the independent variables. If you have many, just list them here with a space between them. So our independent variable is dist in this case, and enter. Right, here's the result, and what we are interested in here, as the question asks us, is to look at R squared. So let's look at an adjusted look at the adjusted R squared, and it's this one here, and then notice that there's not much difference between them. This is because we have a large data set. So 3,796 students, number of observations, so that's a large data set. Usually you don't see much difference, but usually if the data observations are a small number, then they differ, certainly differ. So you can check it or experiment it with different data sets, and you will see, just for fun. Yeah. So adjusted R squared tells us that around 0.7% of variation in Y, or in other words, variation in education, years of education, is explained by variation in distance. So very tiny fraction of variation in this number of years of education is explained by. So that doesn't really mean that our coefficient of interest, which is the coefficient on the distance variable, is not significant. It could be, and it may not be, for different reasons. So this doesn't imply anything yet. It just implies whether the model is appropriately explaining the, or has a explanatory power as a whole, has an explanatory power on the education variable. So well, it looks like it doesn't have much explanatory power, so we'll have to do something to improve it, or maybe we can leave it as it is in case we suspect that we think that we don't have to do anything. Let's look at this, and we'll come to this later. Now, by the way, so standard error of regression is this value here, and usually standard error of regression is a dispersion of Y values along the line of best fit, and this value will go up if R squared is low, and it's also a measure of best fit again, and if R squared is high, this value will be lower usually. So they go inversely, so they have inverse relationship. Now let's look at the coefficient of interest. Here we have a constant here, 13.95 years, with the distance having a coefficient of 0.07, negative 0.07. Now basically, in case you live next to the college, in other words, the distance is 0, then a person will typically have 14 years of education. This is 14, I would say 14. So 13.95 basically is 14 years of education in case the distance is 0. So it's like you're living adjacent to school. Obviously not necessarily, but yeah, since units of measure scale is tens of miles, I think if you are reasonably close to the college, then you should be having you should have 14 years of education, complete education. Now let's look at statistical significance. Standard error is reasonably low, actually I should say quite low, and t-stat, because of low standard deviation, you will get a high t-stat, and 5.34 is quite high t-stat. This implies statistically significant coefficient on the distance coefficient. So yes, there is a very statistical, a very high. No, I shouldn't say very high. It is a significant. The coefficient is significant, so effect is significantly different from 0. And I explained it how this works in manual calculation of p-values and t-values. So p-values always corresponds to this interpretation, or is in line with the interpretation of t-stat. So 0.00, something there is hiding. We don't know, but it doesn't produce a report of a full p-value. You can actually look up the p-value by taking the t-test t-value here, and in the standard normal distribution tables you can find what the p-value is. But basically this is a very tiny amount, you will see. Now the question also asks for the confidence interval. Given this confidence interval, we can expect 95% of the time to have the true beta or population beta to lie between these intervals. So that's what confidence interval does. It just gives you a basically this is a point estimate. So it gives you just estimate the effect of distance on uh, on education, but confidence interval gives a range of them basically, and then in this interval lies the true effect or true beta lies. This is an estimated beta using the sample, but true beta based on these results is basically could be anything between -10 to -0.4. So it could go as high as -10 and as low as, well, it's the opposite of its negative sign here, as low as 0.046. So that's the interpretation of this. A very informal interpretation, obviously, so you need to write a good essay in the exam in case something like this is given to you. You won't have to run a regression, but you will be given an output and asked to interpret the results and comment on them. Now, formally, it looks like an extra 10 mile increase in the distance would result in a reduction of your oral education by 0.07 years. So times it by 12 to get months, so you will get that result. Okay, now we could try and add something here, some other variable, to see if we are suffering from omitted variable bias. What we do is now next is if we insert or we add a control variable where we will control what they do is, what control variables do is, we are not interested in their effect on education, but nevertheless they affect education. For example, if your father or mother had a college degree and then you are about to start a college degree or start working or going after 19 years of schooling, you might be or you might want, you are 5 years old and you could either go to college or you could stay at home. And if your father or mother had a college degree, they know the value of the degree because they experience how it helps them to have a good career or do something and win a Nobel Prize maybe. So there's a high likely chance of you going to school because your father and mother or both of them had a degree, compared to someone who hadn't a degree and their kids may not go because they think, well, they've never seen a college, so they won't understand how valuable the college degree is. So let's do this now, because college degree, this is a variable that will affect education for sure, a number of education years you have, but it also at the same time might be correlated with the distance as well. So let's add that variable and then see and control for that variable's effect, and then see what happens our distance as well, distance effect of distance. And if it changes significantly in the practical sense, not statistical sense, and we might be suffering from bias. So the coefficient may be low because we haven't included enough regressors, independent variables, to control for various effects. At the moment, we only have distance to control. We're looking at distance, but distance is not sufficient explanatory power. Doesn't have it explanatory on education as this suggests. It doesn't necessarily suggest distance is not significant. It is significant statistically, individually as well, but as it doesn't offer a big enough sufficient explanation for a number of education. So we'll control for various ones, but let's start one by one. So now distance, I add now that college, so I'll come here, that college, and double click, yeah, and enter. Done. Right, so let's see what happened to R squared. R squared is higher than before, so that's a good thing. It's just that college is contributing a little bit more, not a huge amount of variation that can be explained by that college, but taken together, that college and distance, basically as a model, they can explain, well, 8%, 9% of variation. So this is a big jump, but it's not as big as we could expect. So 9% of variation in education years can be explained by the model here with distance in that college. Now, when you interpret this sort of multiple regression results, and you don't have to interpret, because the coefficient of interest, effect of interest, effect size we are interested in is a distance. So we can ignore this. In other words, we don't interpret this basically. How you do this is this then. Distance is actually, yeah, t values is showing us that p values are showing us that this is a statistically significant coefficient. Now, when you interpret it, is this distance has a statistically significant effect on education when we control for that college. The effect is this: for additional 10 miles of distance, number of years of education will decline by 0.04 or 0.05 years. So then next thing is that you have to say that when we control for that college or other factors such as whether person's father or mother had in this case, father had a college degree. So controlling for college degree, family member with a college degree, we could expect the distance to have a slightly higher effect than before of 0.0, lower effect than before, 0.04 years of education, right, for a 10-mile extra distance. Now let's add something else. We'll see what happens. So there is a almost, actually this is a big chance, I mean chance that there is a big high probability of having a omitted variable bias here, because it used to be, when we ran this regression, it was 0.07. Now it's almost half, isn't it? Not half, obviously. There's a 40% decline in the coefficient here. If such a big jump occurs in your, I mean, if you observe such a big jump in your regressors coefficient estimators, then you have to add more and more and see how it goes with this coefficient here. If it keeps going down and down, and when it stops, then you should stop adding variable as well. And you don't want to add too many variables as well. It will complicate the right hand side of the equation with multicollinearity among the variables. So here let's add some more, and your book says we have to add more. Actually, let's add more of these. Let's say where the person is black, Hispanic, and then female. I should have had female. And whether the income is high, he lives in household is a higher income household or low income household, and then there is unemployment rate in the 80s, and this is, I cannot remember what it is, but it's included as well, so we'll include that as well. And whether the person lives in a own home or on a in a rented apartment. So let's hit enter now. Right, so here is the result. Now adjusted R-square shows a 10%. That's a huge jump actually from the original one. So we added more, and we are getting more of an interesting result here. Now I forgot to include the by test, so let me put it back. Let me add that as well, and then let's see what happens then. So I have by test now. I guess I included everything now as instructed in your question. So let's try again. Right, and now I think it's complete. It does look like complete. Now this is important to look at now, at this thing here and at this thing here. Adjusted R-square is now huge, a big jump. That's a statistically significant jump if you measure it by statistical significance. Now 28% of variation in education years completed, or student completed in America, let's say, in this sample, are explained by variations in the model, basically in this model. So model has a bit better explanatory power. Now what is interesting is this variable as a coefficient here, minus 0.03. Originally we had minus 0.07. So in case we didn't have anything and single variate regression we ran, this would be the effect. But this is a large, more than 50% decline in the effect, isn't it? So we can conclude that there was the coefficient estimator was suffering from omitted variable bias, because we put back is these omitted variables. The bias is now gone. Maybe there is more, but we only have these control variables that are associated with distance and at the same time has an impact on number of years of education. So when we entered these omitted variables initially in the first regression, these omitted variables were in this case were in the UI hats. So it was absorbing them. And at the same time, because they weren't included in the regression, the effect of these variables were absorbed by this coefficient as well. So that's why you have an upward sort of in an absolute value here, absolute magnitude here is an upward bias. Now once we add them all, we get each of these coefficients now have their own effects, and then if we control for them when we interpret distance, now we get a much more not unbiased kind of coefficient estimator here. So and at the same time, this result is significant statistically at the 5% level, not 1% level, as you can see. And at the same time, if you can see at the 5%, 95% confidence interval, we have no zero inside this. No zero is not included in this band. And notice what happened here is this. Coefficient range, sorry, the range, not range, the bounds have different values than they had before. Let me have a look. Yeah, no, not this one. Yeah, here they had a completely different looking band. Now we have a different band here. So actually the impact is more or less much more less than what we used to see before. This was 0.10. Now the true effect could be actually as high as 0.055 years negative, so negative effect. And usually when you interpret this, you talk about this first of all, you comment on this, and you add this term controlling for variable names, basically that college, other variables like whether the person is black or Hispanic or a female or so on and so forth. So you have to kind of mention them, or if you want it to be short, controlling for other variables or covariates. That's another way. Or controlling for variables associated with distance, and at the same time that could affect the education years, schooling. So in this case, you could say that for extra 10 miles of distance, and education would decline, or decreasing number of education years, or years in high school, or number of years of education, in other words, would decline by 0.0, would be expected to decline by 0.03 years when controlling for variables that might have effects on higher education years on their own, basically. But you don't write on their own thing here. To be more book language or to be more specific, you don't write the individual effects of these, and we don't actually look at their individual significance or whether they are significant individually or not, because we are not interested in them. All we are interested in this distance variable and how it might be associated with number of education years, or number of years you had education in the past, or a student could have in their high school and college years. Now all of these control variables are statistically significantly different from zero, if you notice here. In case you have more of these and some of them, let's say, are not statistically significant, it's important that you delete them or you just remove them, because they don't add any value. In this case, do not contribute to the increase in R squared, or do not contribute to the explanatory power. Usually with the well, all they do, maybe they actually have cause multicollinearity in case that happens as well. And sometimes you don't see a appropriate sort of proper sign, correct, economically correct sign here. Let's say if this is a minus, well, oh, this is positive here actually. I think it is an unemployment rate in the 80s. This is a positive for a reason, because if there is a high unemployment, a lot of people go to school, especially students who consider to work will decide to go to school, and that's a positive effect here. If this is negative, let's say, you will be concerned, because you want to make sure that these variables actually do not correlate between themselves highly, because if they do, then you need to remove one of them or two of them, so that this will have accurate result, positive result, or an appropriate sign here, and then this will not be biased as well, because it will also be affected with if there is a multicollinearity in this. And you had this multicollinearity concepts in your classes, sorry, in your lectures. So that's it for now, and I think as I didn't didn't do a formal way of, I mean, explain you how to write an essay. I know you know, and then I'm aware that you know how to do this. And very quickly, apparently, question number G asks what the meaning of that college being included there, why we included it. Then let me read it quickly. The value of the coefficient on that college is positive. What does this coefficient measure? Okay, right. So this is positive, and they asked us in the question, what is the meaning of this? Basically, if you know, that college is a binary variable. It's where the person, if a person's dad, students had father had a college degree, this value will be 1. That college will take 1. Otherwise, it's 0. So, um, compared to a student whose father doesn't have a college degree, a student whose father has a college degree will go to school 0.69 years more. So they will have basically this student whose father has a college degree are more likely expected to have higher years in education or in school. So everything else being held constant, or we controlling for everything else, this is the effect of that college. Basically, having a father with a college degree, you will, if you have a father. This is a sample specific result here, but assuming we can generalize it to today's. To today and to everyone else in the population. In that case, this would be, we can expect that if someone's father had a college degree, we can expect that student to have longer, on average, 0.69 years of higher education in their portfolio compared to the person who doesn't have whose father doesn't have a college degree. So that's the interpretation of this. Well, it's a bit of a lengthy interpretation to give you more intuition, but I'm sure you understood this. If you don't, let me know. I will explain in the class, or may have to record another video using such variables, binary variables. Yeah. Okay then. Oh, there is another one here very quickly, that the person is black. If a person if a student interviewed in this sample is a black, then this value takes 1. This variable takes 1. If a person is not black, it will take 0. So the interpretation is this again. You compare it. Basically, result is this. I shouldn't go into more details. It gets a bit complicated. So a person, if the person interviewed is black, then they will have 0.36 or 37 on average years of extra education than a person who is non-black, holding everything else constant. That's again important part of it. So we control for everything else when you interpret this specific result, right? But do not interpret 2 results or 2 coefficients at the same time. That doesn't make sense. That doesn't work in the context of linear regression, at least. Okay, that's it for now, and I hope you don't get bored by watching half an hour long videos, but I try to give more intuitive answers to the questions, and it will take a bit longer time, and I keep repeating. Okay. All right, see you in the classroom. Hopefully I'll record another video.